Hello, we're going to talk about 12.1 complex numbers as vectors. Now, recall in year one we talked about complex numbers, and we knew we can represent a complex number, and a complex number is a plus bi, where a is our real part and b is our imaginary part. And this is our notation to represent, our parts of a complex number. And this means the real of z is a, and the imaginary part of z is b, and then we can plot these complex numbers on something called the Archon diagram, or the complex plane. We talked about that, where this is my real axis and this is my imaginary axis. So we'd have to go from the origin, go over 8, then up, go over a units and then up b units, and we get our complex number z right here. And we're gonna in the future you're going to see we're going to represent these complex numbers in terms of theta, right? Theta and r, or something we call our complex, and this is what we call, not our complex, I mean our modulus, and this is what we call our argument. And those are just fancy words meaning, the radius of this, or the length of this vector, and the angle between the vector. So, and there you go. So, but for right now, this is basically this is what we're going to use throughout complex numbers. Now, basically this, a complex number is a vector that goes, a units over and b units in the y direction. So this vector represents this complex number, right? So its position. So and so this means all these properties pretty much from what we learned in vectors hold, right? We can, z1 plus z2 is the same as z2 plus z1, and we can, use the proofs that we showed in vectors to show it, and it's associative. Basically, you can have the properties hold when if you take some vector, right, and we call it z1, and then we add some other, if this is z1 and z2, right, we know that this will be our another vector, our other complex number z1 plus z2. So all those, we can use the triangle rule, or vector addition, and those rules hold for complex numbers, right? So we can take their real parts and add it to their imaginary parts and add them to end up to get this other complex number, right? This one right here, the null vector represents the complex number 0, 0 plus 0i. You can see that's pretty straightforward. And then it says if z is equal to a plus b, the opposite of z would go the other way. So what ends up happening, if this was a plus bi, the opposite of that, right, would end up going something like that, right? Where, it would just go in its opposite. So if this was z, this would be negative z, and that's what ends up happening, right? The magnitude u is associated with a plus bi, and we can see how that ends up happening, right? If we take the magnitude, right, and this, we're going to see that this is this little r, this distance is going to be the magnitude of that complex number, and we can use this formula, right? And so that's what the magnitude of a complex number is. The magnitude of a complex number is going to be the square root of their real part squared plus their complex part squared. The subtraction of two complex numbers is defined by the sum z1 with its opposite of z2, right? So, and that holds from vectors, and we've seen that before. So a few other properties that we're going to look at. Let's look at this one, right? Now this holds from, if we look at a complex number, let's say if I give you a complex number z, and what would happen if I take 2z as a vector? If these were vectors, right, and you had let's say a vector that looks something like this. Let's say that this is our first vector, right, z. What would happen if I take 2z? Well, this would just double in length, right? And so 2z would be this vector, right, from here to here. And those properties all hold when we take multiplying by scalars, right? We can just keep scaling them. Or if we take its opposite, it goes the opposite direction like we showed before, and so on and so forth. So all these properties hold. Now these ones here, this guy right here stands for the conjugate, right? So if you remember that this symbol means the conjugate, right? So if I have some complex number equal a plus bi, right? What's the conjugate of z? Well, that's a minus bi, right? But here it tells me to take the conjugate of the conjugate, right? So if I take z conjugate and make it its conjugate, right? Well, it goes back to a plus bi, or the conjugate of a minus bi is a plus bi. So basically we've shown that if we take the conjugate of any complex number, we end up with just the original complex number, right? Now, if z is the element of the real numbers, right? Well, that means my z is equal to a plus the imaginary part has to be 0, right? And if I take the conjugate of that number, right, that's minus 0, so it's just going to be a anyways. So it's just equal to z, right? So if z is any element of the real numbers, the conjugate of z is just going to end up being z anyways, right? And no matter what, if we have the conjugate, right, of some number, so their magnitudes are going to be equal, right? Because if you have some complex number, right, that looks like this, let's say that's z, right? Right? Its conjugate of that just means its real part is negative, so it's going to end up having the exact same length, right? So z conjugate, go right here. But these two values, these two distances here, their magnitudes are going to be completely the same, so you can see how that happens. Now, moving on, let's go ahead and look at this 12.2. It says complex plane in polar form. Now, we've gone over the Argonne diagram, right, and we've talked about how we're going to represent it in our angle between the complex number and what we're going to call our modulus, right, or our argument and our modulus. Our modulus is basically our magnitude, right? So if we have a complex number z, a plus bi, in Cartesian we'd have some x distance and some y distance. In this situation it should be a and b, right? But we'd have a Cartesian point. But when we talk about polar coordinates, we're not going to represent it by how far we go over an x and how far we go over a y, or how far we go over in a real axis and how far we need, or what direction we need to go in imaginary. We're going to talk about its magnitude, or its modulus, right, and its angle between it. So when the notation that we use is we say theta, or whatever you want to call that. When here we called it theta, and it's the argument of z. That's called the argument, and that's just the angle between the vector. And then our r is our magnitude, which we represent our modulus. So we can plot, when we have used this notation, we could tell us, we know how long what our modulus is, the length of our vector, and we know the angle that we have to go. So, and we're going to use this to be able to plot complex numbers in the polar axis. So, see an example. Let's look at this one. It says, example 1, represent these complex numbers in the plane. So I am going to, I'll use that color. So the first one, A, it says Z1 has a radius of 2, or a modulus of 2, and it's a 60-degree angle. Well, I can see that a 60-degree angle would end up right here, right? But it's got a length of 2, so I'll go 1, 2. So right there, that's Z of 1, right? I can plot that out. Now this is a nice gram. You might have to do this on your own and go from there. Now the next one has Z of 2, and it's my modulus has a length 3, and my argument is negative pi over 4. So that means I gotta go negative pi over 4 is right here, pi over 4, but it's a length of 3. So 1, 2, 3. So right there is Z of 2. My bad, Z of 2. So that's my point right there. Z of 1 was right here. Z of 2 is here. Now this one has a length of 1, but an argument of 7 pi over 4, right? Well, 1, 2, 3, 4, 5, 6, 7. It's actually in the same plane right here, but it only has a length of 1, so that's right there. And that's Z of 3. And there you go. And thanks, guys.